Hello and welcome back, everybody. In calculus today, we're going to, well, not necessarily talk about a certain section, but rather we're going to look at an overview of a certain chapter, and this chapter is namely chapter 5. So I always felt like that in the past, there's a disconnect in this chapter because all of a sudden we're learning about something that is derivative, and the next thing you know, chapter 5 comes along, and then all of a sudden the shift goes to the area under the curve. What's the relationship between the two? Why is it that we're going to change all of a sudden from looking at rates to area under the curve? So that's what this I guess video is going to be about. It's going to look at the connection between the two, and why is it that we're learning this thing called FTC 1 or FTC 2, short for Fundamental Theorem of Calculus, all of a sudden, and what does it have to do with all the stuff that we're learning about when it comes to the area under the curve? So here, let's go ahead and get started. And yeah, hopefully by the end of this session, you will have a better understanding of as to what's happening. So at the beginning of chapter 5, what we did was we introduced a notation over here that represents the following. So R, which is a finite number, is equal to, and you have this weird little symbol from a to b of f of x dx. Now, what is that interpreted as? We learned that that represents the area under the curve for the function of f of x from a to b as our boundary. So that is the meaning of this funny looking shape right here. Now, there is a name for it, and that name is called an integral. Okay, so those two are basically just chained to each other. Whenever you're saying you are going to solve for an integral from a to b of f of x dx, you're really just saying you're solving for the area under the curve for f of x from a to b. Okay, so that's the representation for it. So you can kind of see it over here on the right-hand side. I drew the picture of that. We have f of x as a function, and then we have horizontally bounded from the left by a, bounded to the right by b, and r is going to be this region that's over here. Now, in terms of how do we solve for that area, well, if f of x is very simple for the most part, like say a linear equation, then we would have no problems whatsoever. But unfortunately, we know by now that functions are never that simple. So then that means that we have to find new ways of solving for this thing that we want, or maybe find a way to estimate what we want. So in the first section, what we did was we said, hey, let's go ahead and make some partitions so then that way we can estimate what is the area under the curve. So when we say make partition, that means that you have something that looks like the following. Okay, so you can see how these rectangles, if you add them all up, these are the partitions that I was talking about. If you add them all up, that will give you kind of like a representation or an estimate as to what the curve, the area is going to be. So in terms of our methods, we can create rectangular partitions just like we did. So that will give us an estimate as to what the area under the curve is. Or we can create trapezoidal partitions. So rather than having, like, say, rectangles, we can have trapezoids instead. And that in itself, geometrically, you can see it's definitely a lot more accurate than rectangles. Now, the methods that we have right there, those are methods that you can actually do by hand, because if you only have, like, say, 2 partitions or 3 partitions, that's easy enough. But, if we want to be accurate, as accurate as possible, if we want to make this so that it is, very, very close to the answer, then that means we're going to have to use infinite number of partitions, and that's going to be impossible by hand then. So that is going to be our 2 ways of solving for the area under the curve at the very beginning. If we know what the graph actually looks like, and if it's a geometrical, shape that we know of, like say, for example, a circle or some rectangles or maybe some triangles, we can also figure out what the area under the curve is going to be then. So those are the 3 main ways of solving for this integral that we've been talking about. Now, that is going to be very limited because, again, these are things that we can do by hand. What I would like to do is I would like to still be able to solve for it using some other method that could be exact or precise. So in the next section afterward, we learn to write each integral as a limit. Okay, we learn to write each integral as a limit. So whenever we have the integral from a to b of f of x dx, we can look at it as an expression of base times height, because that's going to be that rectangle. And the summation of every single one of those base times height would then give us the area under the curve. Now, having to do like a few examples in the section, if you want to go back to that video to take a look at it, we concluded that the second equation right here, can be derived into this equation over here, where you can kind of see the base is still going to be the function part, and the base is going to be the b minus a divided by n part, and then the height is still going to be represented by the function, and the sigma notation is to represent that I want as many of these partitions as much as possible. The limit as n approaches towards infinity in the front is to indicate that I want infinite number of partitions, if we can even do that. So here, just giving you a example of it, you have the area under the curve from 7 to 10 of the square root of x squared plus 1. We can then write that as a limit notation. And what this allows us to do is to now take this and throw it into, like, say, a computer program or some sort of calculator, so then that way they can solve for it while we basically just sit back and see what the result is going to be. So this is going to be kind of like our one step up from what we can do by hand, because, we're only limited by how much work we can actually crunch out. And unfortunately, in this case, it's not going to be a lot, as we have an infinite number of partitions. So we are now kind of like, progressing towards how to find the area under the curve a lot more and more accurately. But still, it's not good enough, because ideally I would like to be able to solve for the area under the curve without having to do all that extra work, right? Without having to use a calculator. So is there a way to do that? So that's where we come along and introduce something called FTC number 1, sort of first fundamental theorem of calculus. Now, since it's called the fundamental theorem of calculus, then you might think that, yes, this is going to be something that is important. And in fact, it definitely is, because this is what it's saying. Here you have capital F of x is going to be denoted as the integral from a to x of f of t dt. If I take the derivative of capital F of x, it turns out, according to the first fundamental theorem of calculus, is just the same thing as lowercase f of x. So what that means is that if I have a capital F of x and I try to take its derivative, then the derivative and this area under the curve, or this integral, quote unquote, if you want, they cancel each other out. So that's something that's actually very interesting, because now it's linking back up to what we learned from all the way from chapter 4 and chapter 3. Why is the derivative always what does all of this have to do with the derivative? Well, there's the answer right here. Okay, we've learned about how to take the derivative, but we never really learned about what happens if we go backwards. In math in general, the way you can think of it is there is addition, so therefore there's subtraction, because they are inverses of each other. There's multiplication, and then there's division, because they are inverses of each other. There's derivative, and then now there's integral, because they are going to cancel each other out as well. So here, the best way I can explain it without having to do a proof, because the proof is a little bit more tedious, here you can see, here's what I'm going to do. I'm going to go ahead and say that let t be in terms of seconds, and let f of t be in terms of meters per second. So if you look at capital F of x, which represents, again, the area under the curve from a to x of f of t dt. If you're thinking about the unit of what is going to be underneath the curve right here, well, keep in mind, this area underneath the curve, it's really still bounded by the condition that it's just base times height, because you have a whole bunch of these partitions added up. Well, take the unit of the base, which is a seconds. Take the unit of the height, which is in meters. So if you take meters per second multiplied by seconds, then you can see that the unit for this f of x thing is going to be in terms of meters. Okay, so that is how we can look at it geometrically as to what the unit is going to be. Now, x is still going to be in some sort of time, because x is going to be a variable that is on the horizontal scale. So that is still in terms of seconds. So as of right now, capital F of x is in terms of meters, x is in terms of seconds, and if I now consider taking the derivative of the derivative of f of x with respect to x, then that means I'm taking the derivative of a function that is meter with respect to time. And that unit right there will then go back to meters per second, which means that, hey, we are now going back to the original function capital F of lowercase f of t. But now thinking a little bit further, know that whenever we're solving for a derivative, we're looking at an instantaneous moment. So then that means we're solving for what is the value of what is the value of x at f of x over here then? So I want to know what that y value is going to be, okay? All right, so again, the conclusion out of all of this is that FTC1 over here, the derivative and the integral, aka the area under the curve, cancels each other out. So that is the big conclusion that we're getting from FTC number 1. As of right now, we can then go ahead and go into some of these examples that we did in the book, where you can see FTC number 1 in action. Unfortunately, a lot of these problems right here, this is what we call masturbation, because it really doesn't really relate to any kind of word problems or anything that's applicable. But it's just to make sure that you can manipulate FTC number 1, so then that way you can use it in the near future to proving maybe something that's more useful. So over here, for example, in the first case right here, according to FTC number 1, if g of x is equal to that integral, then g prime of x, then that is just equal to ln of x then, according to FTC number 1. Then if you go to the second one right here, we can go ahead and solve for h prime of x. H, if you look at it, is going to be kind of like g of x. So this right here, this is g of x squared, because you'll notice that g has an x right here, but instead, because I have an x squared, then by substitution, then h of x is equal to g of x squared. And so now h prime of x, if I want to solve for its derivative, then it's equal to g prime of x squared, and by the chain rule, we multiply by 2x. And now making a substitution, then that means that we have the following over here, ln of x squared multiplied by 2x. So you can see how the chain rule is still applied to FTC number 1. And finally, for this last one, not to spend any time, but this is what you're supposed to get as a result. You're supposed to get x squared minus 1 quantity squared multiplied by 2x, and then minus 3 to the x minus 1 quantity squared multiplied by 3 to the x multiplied by ln of 3. So all of this right here, again, as I said, it's just masturbation, because you're not really getting any kind of like significant representation of what I really want. But there is some, silver lining to all of this, because, masturbation is not necessarily a bad thing. It turns out that if you look at the last example, this gives us an idea as to how to actually solve for the area under the curve, which now leads us into something called FTC number 2. Because, this entire time that I've been talking, I still did not really answer my original question. How do you solve for the area under the curve using all of this FTC thing? Because, we know that they cancel out with a derivative, but great, how do we actually use it? So that's basically going to be our big finale over here. What does all of this have to do with solving for the area under the curve? Well, this is where FTC2 comes in. FTC2 is defined as the following. Well, it's not defined, but it's going to be proved as the following. The area under the curve of any function f of x from a to b is going to be equal to capital F of b minus capital F of a, where f is the lowercase f is the derivative of capital F. Or if you want, you can say that capital F is the antiderivative of f. So that right there is going to be our key then. So what that means is, if we want to solve for the area under the curve, all we have to do is find that antiderivative equation, plug in the upper bound, plug in the lower bound, and subtract one from the other, and we're good to go. So I'm not going to go into the proof right here. I wrote it all down, and I proved it in another video. So if you want, you can pause it and take a quick look at it. But we talked about this in the past then. So this right here is the whole thing, and then this again is going to be our conclusion. So that's going to be our proof. So the next time you're solving for the area under the curve, what that means is you can set up the integral for it, and the way you're going to solve for it afterward is to solve for the antiderivative. So here's an example. Solve for the area bounded by the curve of y is equal to 4 minus x squared and y is equal to 0. So I drew the picture of it over here on the right-hand side. You can see the region that we're talking about, where the upper bound is going to be the curve and the lower bound is going to be the x-axis. In addition to that, I found out where are the zeros, which will be 2 and negative 2. So that's where I came up with this integral right here. So the integral from -2 to 2 of 4 minus x squared, that is going to be my representation of the area under the curve that I want to solve for. According to FTC number 2, all we have to do now is take the antiderivative of this equation. So I want to know what function has a derivative of 4 minus x squared. Well, that's where this guy came in, 4x minus 1/3 x cubed, because you're doing the power rule backwards. And now, according to FTC number 2, I'm going to take 2 and plug it into the equation. And then I'm going to take -2 and plug it into the equation. And then take 1 minus the other, the upper bound minus the lower bound. And be careful about this arithmetic over here. It's not even algebra. If you can clean that up, then that means that your answer, this 16, is going to be the area underneath the curve then. Okay? All right, so here is the final example of what's going to happen then. Suppose this time that you have lowercase f of x is equal to the square root of 25 minus x squared, and the derivative of capital F of x is equal to lowercase f of x. If capital F of -5 is equal to 7, then I want to solve for what is the capital F of 5. One way that you've learned to do this is to find the antiderivative of this equation, f of x, and then put a plus c, and then solve for what that c is equal to by putting in the initial condition of f of -5 is equal to 7. But unfortunately, that's easier said than done, because trying to find the antiderivative of some equations, we can't quite do that. And this definitely is going to be one of them. Okay? But what we can do is we can use FTC 2 to help us out a little bit. According to FTC number 2, here's what I can set up. The integral from -5 to 5 of 25 minus x squared inside the square root, that is supposed to be equal to capital F of 5 minus capital F of -5, right? According to FTC number 2, all I have to do is just solve for the antiderivative, plug in the upper bound minus the lower bound plugged in, and then hopefully that'll be our answer. Now, as we said, capital F of -5 is equal to 7, so I can make that substitution here. What I want to solve for is capital F of 5, so I'm going to leave that alone. This guy right here, now keep that in mind, that this on the left-hand side over here, that is also the same thing as saying find the area under the curve from -5 to 5, because again, the area under the curve and the integral are one and the same thing. So on the right-hand side, you can see how I drew that picture then. So this guy right here is basically going to be this right here, the area of that, if we can find it. And I think that's easy enough to do, because that is supposed to be a circle. That circle has a radius of 5, so the area is going to be equal to 5 squared times pi divided by 2. And then now I'm going to go ahead and plug that in as my integral over here. So 5 pi over 2 squared. Or if you want, you can go ahead and say 25 pi over 2. And now f of 5, the answer is going to be then 25 pi over 2 plus 7. Notice the entire time, I didn't even solve for the antiderivative of f of x is equal to square root of 25 minus x squared, because, well, it's impossible. Well, it's not that it's impossible, but it's not possible with the number of tools that we have right now. All right, so hopefully this was helpful. Thank you so much for watching, and thank you for getting through to the end of this video. So, if you like it, then, put a thumbs up for it, because hopefully I'll have 100 likes by the end of the 2030. All right, talk to you later. Bye-bye.